Hello, everyone. How's it going today? My name is Christopher Poyser, and today we're going to be going over the wonderful and amazing topic of semaphores. I know, exciting, right? Today we're going to be going over some background behind semaphores, why it was invented, what exactly is a semaphore, why do we need it, and give you guys a few examples to see how you can implement it in some of our programs. And then I'm going to give you guys a problem so you guys can come up with a solution for it. So without wasting any further time, let's get right into it. All right, let's quickly go into the background and dive into why exactly a semaphore was created. So I'm going to assume everyone is familiar with the topics of processes and threads, and we've now learned that certain operating systems may split these programs into different processes and threads to maximize efficiency. But one known aspect of this, when you split programs into different processes and threads, is that we may end up sharing resources. And what I mean by sharing resources is that two different processes or threads may try to access the same piece of memory, such as a variable or so. Or another way to think about this is that a certain resource or variable may perform multiple operations in one process or across various processes. This will create a big conflict though down the line when multiple processes are running concurrently and they're attempting to access the same resource. Because let's say you're trying to decrement a list from 10 to 0, and you have two different processes doing the same thing, decrementing the list. You may end up in a situation where instead of going from 10, 9, 8, 7, you go from 10, 8, 7, because the two different processes decremented the same variable at the same time, thus skipping 9. So what we were previously discussing was the amazing concept of mutual exclusion. So if certain threads were to execute, they can access and modify a resource concurrently, thus being in the critical section where various inconsistencies can take place. So certain sections in the program have a critical section where various concurrently running threads may not execute at the same time. So a critical section is a piece of the program in which processes or threads access a shared resource. Only one process or thread can possess the mutex at a time. So think of it like a lock. Mutex is another word for mutual exclusion. If I have the lock, no one else can have the lock, thus no one else can access the resource. So when a thread or process is accessing the resource, it has to lock the mutex to prevent other threads and processes from concurrent access of that resource. And upon being done with that resource, the thread or process unlocks the mutex and gives the lock away, so another thread or process can possess that. But not only can these threads not enter the critical section of the program at the same time, these processes must be ordered and executed in a proper sequence to avoid a race condition. And the race condition, as we know, occurs when the various threads access and modify shared data at the same time. But because we don't know how the operating system schedules the threads, you don't know the order in which the threads will attempt to access the shared data. So what I have here is a few funny pictures to give you guys an example, visual image of what we want and what we don't want. So what we want is only for one thread or process to utilize that resource. As you can see, one person's using the washroom while everyone else is queued waiting to use that resource. What we don't want is various threads or processes attempting to access the resource at the same time. As you can see here, two different people fighting over a cookie, the plate of cookies at the same time. The plate is the resource, then taking away the cookies at the same time is them modifying it, and that's what we don't want. So now you might be asking, what exactly is our solution to enforce mutual exclusion? That's right, ladies and gentlemen, semaphores. So semaphores is just a signaling technique. By signaling technique, it just means which process or thread it is allowing to pass and utilize that shared resource and which one it is blocking. So it is a very significant technique to manage concurrent processes by using a simple integer value, which is known as a semaphore. So this variable or value is used to solve the critical section problem and achieve process synchronization in the multiprocessing environment. So it is a integer variable where only three operations may be performed on it. So we could define the variable or semaphore with a non-negative integer. We could call semWait or wait function, which decrements the value of the integer slash semaphore, and signal or signal, which increments the value of the integer slash semaphore. It is, however, an atomic variable, which means only one entity or process may utilize and modify the variable at a time, thus providing our mutual exclusion. And we could use a semaphore to enforce a mutual exclusion since it only allows one process to handle a semaphore and prevents conflicts among shared resources, which is what we want. Now, there are two different types of semaphores. The one I'm going to be enforcing and talking about today is the binary semaphore, which is the mutex lock we were previously discussing. It can only possess two values, 0 and 1, and initially it is initialized to 1. And it's used as a solution for the critical section problems with multiple processes, which we were discussing previously. So here, as you can see in this chart, if the semaphore is available, it has a value of 1. If a processor thread called semWait, we decrement that value, and it has the value of 0. And if another process tries to call the semaphore semWait while the semaphore has a value of 0, it will stay blocked until that value becomes 1 again. So it will stay blocked and wait in a queue until it becomes unblocked, and then it will become available. So as we can see here, looking at the chart, we have a semaphore value starting off at 1, and we have two processes. So let's say semWait is called by the first process, and then we're waiting for it to call some signal for that semaphore to be available again. But if process 2 calls some wait as well at the same time, it becomes blocked and must wait until that resource becomes available again. As we see during this period, 1 becomes available, and then it could take over the semaphore and the value becomes 0, and now it could proceed with execution and then call sem signal again, turn the value back to 1. And this is an important part to avoid deadlock. This process must call sem signal again. So how is the semaphore solution more useful than the other solutions? Well, we could see that if we're employing strong semaphores, which is one possible way, we can avoid the case of starvation by employing a FIFO queue. So in strong semaphores, we employ queue, first in, first out procedure, where the first process I called semWait is the first to be executed, and the rest must wait until it sem signals again for the resource to become available again. Thus, we're avoiding the case where the process is waiting indefinitely. Threads waiting to enter the critical section are queued. Therefore, there's no busy waiting since they are not running on any CPU core, which is another important factor. But one major factor we must be aware of is that deadlock is still very possible. Thus, we must order sem signal and sem wait in a way to avoid not releasing the resource.
All right, so let's go over an example real quick. So right here we have a two-process barrier example, and right before I get into the problem, let me give you an analogy real quick. So let's say you and your friend message each other and you want to meet each other at the ticket booth at the movie theaters. You both are going to go watch a movie, but let's say one friend is going to arrive earlier. So you tell that friend, can you wait for me at the booth before you go in? So that friend is going to be waiting at the booth where they give their ticket to go into the movie for his friend to arrive. Once his friend arrives, they can both proceed into the movie theater and they give away your ticket and they go and watch their movie. Same thing goes, or like the same analogy can be made for this example. So here we have two processes executing two different functions. One process is executing A arrival, the other is executing B arrival, respectively. One process can continue to execute its code until the other process has signaled that it has arrived. So let's go over the code real quick. We have two semaphores, semaphore A and semaphore B for A arrival and B arrival, respectively. Once A arrives within that function, we call sem signal A to increment the value of semaphore A to 1. And then we call sem wait on B, and we must wait until B resource comes available or semaphore B's values equate to 1. Once that value is equal to 1, then A arrival can proceed and enter, process A can proceed and enter and execute the rest of its code. The same thing goes for B arrival. We signal B that it has arrived, incrementing the semaphore B to 1, and we must wait until A's value is equal to 1 or the resource becomes available. Once it does, we can pass the barrier. But after both processes pass the barrier, we want to be a continuous barrier, so to reset all over again. So we must reset the resource back to 0 for both of them. So that's what we call semWait A and semWait B. We reset the resource back to 0, and the same function can proceed all over again.
Go through another problem together. It's going to be simple like the last one, and we're going to work through the solution together. So this one is going to be a producer-consumer problem. So one process is consuming data, the other process is producing the data. So one is reading the data, the other is writing the data. They're both utilizing the same block of shared memory. So you can see why we need semaphores here. Only one process can be reading or writing to that piece of shared memory at a time. Process 1 writes data with write data function, and process 2 reads data with the read data function. Using two semaphores, let's come up with a solution here. All right, let's work through this solution together. So let's start right from the top. We have our two semaphores like we discussed before, but notice here the differences. Producer is initialized to 0, consumer is initialized to 1. Right below it, we have our shared memory, which is just an integer array. So let's go through the first process first. We're going to go through write data, which is going to be utilized by process 1. So we can see here it does some wait on consumer. So it waits for the consumer to begin reading. So since our consumer resource is already initialized to 1, that resource is available. So now we can start writing to that piece of memory. So we just have a simple function here, simple write function, temp mem and I equals temp mem and I plus I times 3, just changing the integer in that position. And then we could signal to producer, making the producer resource available now. So we're going to make it from 0 to 1. And since read data and the other process waits on this producer resource to become available to signal that it has written data, once that becomes 1 to say we're finished writing, then we could start reading and start printing out each of printing out the shared memory that we written to. And once we're done reading, now we could send signal to consumer again, making the resource available again. So now we could start writing again, and the whole process continues. This way, only one person is writing, only one's reading. Since one's waiting on the consumer semaphore resource to become available, and the other one's waiting on the producer resource to become available. When the consumer resource is available, that means the consumer is ready to begin reading. That means we can start writing. When the producer resource available, that means we're done writing, and now we can start reading. So this is how the process works in between the two. And that is it, ladies and gentlemen, for today. I want to thank you for watching this whole topic of semaphores. Hopefully you learned a good amount from it, and you could carry it on with you through your day-to-day programming lives. My name is Christopher Poyser, and thank you so much. Have a great rest of your day.